Hi, this is Andrew Wolf. In this video I'm going to talk about the physiology of the EKG. Now the EKG is measured with leads that are placed outside the body, and in this video I'm just going to really focus on the three limb leads. So there's a lead that's pasted up here on the right arm. There's a lead that's placed over here on the left arm, and then there's a lead that's placed down here on the left leg. And these measure the flow of ions in the body, or actually the movement of action potentials. Now, the leads are made up like this. The lead number one is right here. Now, lead number one actually, since lead with Roman numeral 1, actually measures the flow of ions between a negative lead of the right arm and a positive lead of the left arm. So it is because of the way that the electrophysiology works, any movement in the direction of any action potential that moves in the direction of the negative right arm lead and the negative left arm lead is going to be detected as a positive or a deflection of the waveform in a positive direction above the line of 0. And anything that is moving backwards towards from the positive lead to the negative lead is going to be noted as a negative deflection on the EKG waveform. Now, I don't want to get too much into the physics of how this is actually based on. This is actually an oscilloscope that measures the movement of ions in the body, and I'm not going to get into the physics of how an oscilloscope works. But I just want you to be aware that when you have ions, when you have the action potential moving from a negative lead to a positive lead, it is a positive deflection on a waveform, and if it moves in the opposite direction from a positive lead to a negative lead, it is a negative deflection. Okay, now so that's lead 1. Lead 2 goes from the negative right arm lead to a positive left arm lead. So that is lead 2. So again, any action potential moving in this direction, any wave of depolarization moving in this direction is going to result in a positive deflection on the EKG waveform. Now, if we are having a wave of repolarization, repolarization is going to be detected on these leads exactly opposite of the waves of depolarization. So, all right, here, let me explain this here. Okay, so we're going to look at lead 2 here. So if we have a depolarization, a wave of depolarization moving in this direction, it's going to be detected as a positive deflection on the EKG, or the oscilloscope that is our EKG. If there is a wave of depolarization moving in the opposite direction, it's going to be a negative deflection on the oscilloscope. Now, with repolarization, if we have a repolarization moving in this direction, it's going to be a negative deflection. If there is repolarization moving in this direction, it's going to be a positive deflection. Okay, so there's 4 possibilities that get detected in 2 ways. Depolarization, wave of depolarization in the direction of positive to negative is a positive deflection. A wave of depolarization moving away from the positive lead is going to be a negative deflection. A wave of repolarization moving away from the positive lead is going to be a positive deflection, and a wave of repolarization moving towards the positive lead is going to be a negative deflection. So again, depolarization and repolarization are detected, make opposite waveforms on the EKG oscilloscope. Okay. Now, here, let me erase these things. Okay, so wave 3, lead 3, is actually moves from a positive left limb lead, and the left arm lead is actually turned negative, and the machine just does this for you automatically when you ask it to measure a lead 3. Actually, I put the arrow in the wrong direction here. So it's negative left arm lead to positive lower extremity lead, lower leg, left leg lead. Okay, so if you have a wave of depolarization moving in this direction, then it will be measured as a positive deflection. And a wave of repolarization in this direction is going to cause a negative deflection. Okay, so this will make more sense when we start actually talking about the lead. Now again, this is the EKG is essentially an oscilloscope that is drawing on paper, and that is getting drawn on paper by a computer. Actually, nowadays it's just done on a computer. It used to be just a little arm that would move, and we're measuring the flow of ions towards a positive lead or away from a positive lead, and it is measuring this waveform over time. So we have time in this axis, and then a measurement of ions in this axis, the movement of ions in this axis. Okay, so there's one other lead that I do want to talk about because it's very sort of interesting to talk about when we start talking about the actual EKG. There is a lead called AVR. Now AVR is made up of the just the right arm lead as a single lead, and the right arm lead is positive. So there is no negative lead. It's only measuring the flow of ions moving away from or towards this lead. So this is called AVR. And the same principle is true. We have an AVF that's pointing towards a positive lower limb lead, and an AVL pointing towards a positive. So the single leads are always just positive. Okay. And then actually all the V leads that kind of go across the front of the chest, these are all just positive leads measuring ions moving towards or away from them. So these would be the V1, V2, positive leads. So there is no negative lead. So you don't need a negative lead, you do need a positive lead. So again, the limb leads, lead 1, 2, and 3, are measuring the flow of ions between a negative and a positive, but all the positive leads, the AVR, AVR, and this is supposed to be AVL, and AVF, and V1 through V6, are all just measuring ions moving towards or away from a single positive lead. Okay, for this discussion I want to sort of compare and contrast lead 2 and AVR, because in some ways they are almost exact opposites. Not quite, but close. So you can see AVR is going to be measuring things going to and from the right arm lead, and lead 2 is going to be measuring ions that flow in between the negative right arm lead and the positive left arm lead. So these lines aren't quite parallel, but they're close to parallel in pointing in opposite directions. Okay, so I'm going to sort of compare and contrast these two leads. So here I'm going to draw ourselves a little EKG strip, and Remember, this is an oscilloscope. This is 0. This is positive. This is negative. So again, positive is a wave of depolarization moving towards the positive lead, and negative is a wave of depolarization moving away from the positive lead. So this is going to be, I'm going to talk about lead 2 first. Now why am I talking about lead 2? Well, lead 2 is the lead that is the closest to being parallel of the direction of the main flow of depolarization in the heart. Okay, so depolarization in a normal heart starts off in the sinoatrial node, and it travels down, some different pathways to the AV node, and it also travels across the heart here. So the overwhelming, I'm going to draw in green here, the average vector, so the average direction and force of all these three directions of travel is going to be about here, right? So that is the average waveform of depolarization inside the atrium, moving from the SA node throughout the atria and to the AV node. And the AV, I'm going to draw the AV node here. Okay, so what does that look like? So the wave of depolarization in the atria is going to look something like this. I'm going to choose green so you know that it's matching this vector. So you can see that according to lead 2, what lead 2 is picking up here is a general movement of ions from this direction to this direction. Okay, so it's moving towards the positive from the negative to the positive, so that's going to be a positive deflection. So here we're moving along here, and we get a wave of depolarization starting from the SA node and moving down to the AV node, and we have a positive deflection. And those of you who have studied EKGs at all would recognize that as a P wave. Now there is going to be a pause here because the AV node slows down conduction. So there's going to be a moment when there is really very minimal, there's no movement of the depolarization wave. Once we've depolarized the atria, the wave slows down in the AV node. And then after between 0.16 and 0.2 seconds, the wave is going to start moving again. And where's it going to move? It's going to move down the bundle of His and then into the Purkinje fibers, and then it's going to make its way down to the left and right bundle. Okay, but I'm going to stop there because as we have this movement of activity, this generates a mean vector of the flow of ions in this direction. And again, this is very closely parallel to lead 2. So what do we have? We have ions flowing from the negative to the positive. And that gives us a positive deflection in the waveform. Now this is a very rapid and quick waveform that moves down here, so it is very closely parallel to lead 2, so it's going to give a very dramatic and quick deflection. That's why it's so much bigger than the P wave, because it is closely because the average is so closely parallel and because the ions move so quick. Now the ions spread up the left bundle and throughout the atria, right? And the right bundle and throughout the atria. And we have then we have ventricular depolarization. So what does this waveform look like? Well, this average waveform actually looks almost just the opposite of what it looked like when it was going down the bundle of His and Purkinje fibers. So we're going to end up with a waveform moving in this direction, which is a negative deflection. So we have our S wave. So we have P, we have R, and we have S. And we don't have a Q here. Q waves we usually actually don't have in a normal EKG. It's something that that tends to occur when there is evidence of a prior MI. So we tend to call it the QRS, but in a healthy heart, you're just going to have the RS. So again, the R is because of positive deflection with the depolarization going down the bundle of His and Purkinje fibers from the AV node, and the negative deflection of the S is coming from depolarization of the ventricles themselves as the wave of depolarization moves back up from the apex of the heart around the ventricles. Okay, then we're going to have another pause. And what makes up the pause here? Well, remember, if we look at an individual cell, when an individual cell depolarizes in the ventricles, you end up with a rapid depolarization and then sustained depolarization. So the rapid depolarization is from the fast sodium pumps. Then you have sustained depolarization because of the calcium leak. And then you have more rapid depolarization. So from here to here, we have sustained depolarization. So there's no wave, but the waves have not repolarized yet. They don't repolarize until after there's a delay. So we have a delay here where there are no waves to measure. Then we have repolarization of the ventricles. And here I'm going to draw that in white. The wave of repolarization moves across the ventricle like this. And what does repolarization look like? Well, if you have repolarization that is moving away from the positive towards the negative, it is actually going to cause a positive deflection. So we have this average vector of repolarization that's moving away. So instead of having the negative deflection of the S curve, we're going to have a positive deflection. And that is what's going to make the positive deflection of our T wave. Okay? So that is lead 2. So we have a positive P wave as we have here, let me use a different color here as a pointer. We have a positive P wave as with atrial depolarization because of this vector here. We have a delay in the AV node. We have a positive deflection of the R wave and a negative deflection of the S wave as we have the action potential moving down the Purkinje fibers and then back up the bundles and into the ventricles. Then we have a delay as calcium prevents the cells from depolarizing. Here, let me move over just a hair. And then we have a wave of depolarization as the wave of depolarization moves from the apex of the heart up. And that gives us a positive deflection because it is repolarization, not depolarization. Okay, so now let's talk about what a typical AVR EKG strip would look like. Okay, so here we have our oscilloscope, EKG, positive, negative, and this is AVR. So anything going towards the positive lead is going to be read as positive. Anything going towards the negative lead is going to be read as negative. Okay, I erased all the lines in the heart here, so we're going to start all over from scratch looking at the AVR lead. So we've got ourselves the SA node, and we've got ourselves the AV node, and we have an action potential that's flowing through the atria and to the AV node, right? So the average vector here is going to be something like in this direction, right? So I'm going to start off with a little delay before the action potential. So we're going to have the action potential start. So this action potential is moving away from the single AVR positive node, right? We've got a positive node here. It's positive. So you're going to expect there to be a negative deflection in the P wave, right? Now we have our delay in the AV node, and we've got a vector that looks about like that. The action potential is moving from the AV node down to the apex of the heart, and again that is moving roughly in this direction away from the positive. So that's going to be detected as a negative deflection from the AVR, right? Then we've got our action potential moving up the Purkinje fibers and out into the ventricle. I mean, not the Purkinje fibers, the left bundle and the right bundle, and moving up into the ventricles. And that's going to make a vector that looks roughly like that, pointing towards the positive lead. So we are going to get a positive deflection. And then we have our wave of repolarization, which travels across the ventricle, because the cells that were depolarized first are going to repolarize first. So you're going to have a wave of repolarization moving towards the positive lead. And what do you have when you have a wave of repolarization moving towards the positive lead? You get a negative deflection. So you can see the AVR, lead 2 and AVR are near polar opposites. And this is why, because their lines are nearly parallel, not quite, but nearly, and they point in opposite directions. Okay, so I hope this makes sense to you. Please let me know if you have any questions, and if you're please take a moment to give me some feedback by giving me a thumbs up or a comment. And if you'd like to directly access my pathophysiology channel, you can do so on this link.